Hey guys, how are you? It's great to see so many of you here tonight or today. I went to the website just today and I checked the instructions. It says no suits. Exactly. You guys are not disobeying. I am. Okay, maybe you disobey better in other terms than the suit. So I'm not a hacker, I'm a quantum physicist. And I was supposed to tell you about quantum computers and what does it have to do with this topic, like information security or something like that. So I'm not going to go to the deep details of quantum physics, obviously, you know. That's 2 years of university studies. But instead, I want to give you a flavor of, you know, what it is, what's going to happen in the future. It's a pretty hot topic nowadays. And very recently, we got some money to build a quantum computer, like a small-scale quantum processor from these foundations. And, you know, we just made a press release, and I thought, okay, I don't know if people are really interested, but wow, you know, I was in the morning TV and in different radio channels telling about quantum computers, and yet we didn't even do anything. We just got the money. You know, does it just sound a little bit like some sort of hype about, you know, artificial intelligence VR or something? You know, in the conferences, you know, people have nice stands, but, you know, they haven't done any. Well, we have done something, you know, of course. We have qubits. Quantum bits. I'm going to tell more about that. But it's a pretty hot topic. And the reason, of course, is that it's not just, you know, fuzz. There is something to it. And maybe after this talk, you guys know a little bit more what is there to it. Okay. There are some big players also, you know, investing lots of money, you know, 100 times more than what we got. You can see familiar names, you know, these are IT companies that really think that quantum computers will be very important in the future. And they want to keep up. They want to be actually in the forefront of building this device. And in addition to these companies which actually are doing the hardware, there are also software companies. So it's not only hardware, it's also going to software. Just a couple of days ago, the CEO of Cambridge Quantum Computing, which is a software company, visited our labs. And they're really building quantum compilers and stuff like that. You know, it's still in the very beginning, but it's something that people are looking into more and more. You know, now going back from today to, you know, where it all started from. It was only in the beginning of '80s when the first ideas about, you know, that, you know, let's use these quantum systems, the systems we don't really understand that well, for something good, for solving problems. For example, simulating other quantum systems. If we had a quantum system that we could control, maybe we could make that to, you know, to simulate or emulate another quantum system that is of great interest. And quantum systems, you know, everything is quantum when you go deep down. But when the quantum is important, for example, that's important in the atomic level, how the properties of materials, and now fortunately also in electric circuits, when you cool them down to low enough temperatures. I will tell you later. We can get quantum effects, coherent quantum effects there that is really unique and really great potential for quantum computers to build. Okay, so in the beginning of '80s, there was this kind of idea, but nobody knew how. And then, theoretically, about 20 years ago, Peter Shor came up with a famous algorithm called the factorization algorithm. This was the first sort of proof, theoretical proof, that if we had a well-working, perfectly working quantum computer, it would be faster in some problem, this factorization problem, than the classical computer. You know, classical computer I will talk more about this problem later on, but classical computer is very slow in this problem, but quantum computer is fast. Okay, and then right after that, Grover found a way to, it's called a database search algorithm. Basically, in the square root of the time, you can find items from an unsorted database. So these algorithms, what do they have to do with information security? You can actually make attacks against some sort of encryption protocols like RSA. So, and then that's for the factorization algorithm, and then the database search, you can make an attack against DES. Well, here it's kind of a not as serious attack, because if you just double your seeds, double the number of bits in your DES, basically, then you're well off. But in here, it's a more serious problem, because the factorization, the RSA algorithm is based on the idea that factorization of large integers is a very hard problem. If I ask you what's 144, I'm going to factor that. You can easily say it's 12 times 12. But if I give you a 6-digit number even, to factor that in your head, it's very challenging. Even with pen and paper, it's really challenging. You can easily multiply, numbers which are of the order of 1,000, but it's very hard to do it in the reverse. And that's where this public key distribution protocol is based on. So basically, the guy who wants to encrypt, he knows these two very long integers, it's our prime numbers, so you can't divide them by any other number. He knows those, then he multiplies them together, and then he uses that to encrypt. But only he who knows what these two numbers are can decrypt. But that's based on the hardness of the factorization problem mathematically. But the Shor algorithm uses quantum computer in a very specific way to solve this problem, so that it's not anymore exponentially hard. So the time to break this encryption does not grow exponentially when you increase the number of bits in your key or the integer, but it grows grows polynomially instead. So the organizers were telling me that, okay, go also to the details. Don't just talk on a general level. So just for you, I added this stuff here. I'm not going to the very deep details though, but I'm just adding this stuff. I just want to show you that why does the factorization algorithm work, and where is the quantum? So let's say that you want to factor a number, an integer, which is n, it's a number n, it's an integer number. By the way, the screen is somehow a little bad, but it's just n. How you use the quantum computer in the end is that you first pick a number that is integer number that is smaller than n, and then you find the period of a to the power of x mod n. So you can use the quantum computer to find the period of this sort of function, and then using classical computing, you can actually do the factorization. This is obviously not the whole algorithm, but I just wanted to point out that this is where the quantum computer, this is the problem actually that the quantum computer solves efficiently. Everything else is classical in this algorithm. And it's not obvious probably to everybody, or at least most of the people, that why is this basically solving the factorization problem? But that's an hour talk instead of a 30-minute talk or 2-hour talk. So we will not go into that. But anyways, you get an idea that and one more thing is that the quantum computer spends only log n squared, O log n squared time on this. Whereas, as I said, the classical algorithms are much slower. They basically freeze out, so this goes as square of the number of bits in n. So that's not bad. But this is taking that we had a perfectly working quantum computer. Now, what does it take to actually build that computer? Okay, nothing works perfectly in reality, but it still takes a lot, and I will talk about that later. But first, let me give you just like a sort of intuitive idea why in the world quantum computer could solve things more efficiently. And this is the intuitive picture. Think now quantum world as the whole sphere. So I've now just, made a very great simplification so that quantum world, all the states in the quantum world would be the points on this sphere. And now classical world has much lower dimension. So in this sort of picture, classical world would be this arc here on the sphere. So lower dimensional object. And now you would need to, always go from point A to point B along this arc. But the quantum world allows you much more. Quantum computer uses these higher dimensions. Well, the classical world could be only 1 bit, like in a computer. So it could be just 2 points, 0 or 1. If you had a 1-bit, computer, your classical state would be 0 and 1. The quantum bit, instead, can not only take these 2 values, but it basically is a point on the sphere, as I explained in the earlier slide. So it can take any value here on this sphere. So basically, it means that it's an arrow here or a point, and it's defined by 2 variables, basically 2 angles here. And in quantum physics, we basically say that it's a superposition of these states, 0 and 1. That is the most general state of the quantum bit. So there are 2 numbers which define what's the state, C0 and C1. So classically, C1 would be either 1 or 0, and that would determine whether it's a bit is 1 or 0. But in a quantum world, these are complex numbers, and there are some restrictions. The square sum needs to add up to 1, and the overall phase doesn't matter. So there are 2 variables, and that's basically 16 bytes if you use a double precision number to represent a single variable. Okay, that doesn't sound hard. You can do that, by hand or by any computer. If you take 2 qubits instead, the qubit can be the qubit register, which is the 2-qubit system. It can be in an arbitrary superposition to all of the different states of the two bits. So now instead you have 4 numbers, 6 variables, because again 2 degrees of freedom go out, and you would need a 7-dimensional sphere to represent this. The dimension goes exponentially up when you increase the number of qubits. So if you had 1,000 qubits, you would have almost 10 to 300 variables in your classical computer that you would need to represent the state of this quantum register. So if you have 1,000 qubit quantum memory, you can never represent that in a classical computer, because there are less than 10 to 100 particles in the whole universe. So even if you would take every particle in the universe and say, that's my 1 bit, that's another bit, you would still not be able to write down the state of the quantum memory. So this is where, this shows you that quantum computers, or this shows you that classical computers cannot do everything that quantum computers can. It does not prove you that quantum computers can be used for something good. That's where we need the Shor's algorithm, that's where we need the Grover's and other algorithms to show how to use exactly the quantum dynamics to solve some problem. Okay, so in a nutshell, I will just repeat myself. Quantum computing, in the very simplest case, is something. You have a classical input, there's L missing. That could be, for example, factor this integer. Then the magic happens, the quantum dynamics. And that could happen, for example, on this kind of a superconducting chip that I showed you in the first slide. And then you have a classical output, you have the solution. So it really can give you something useful. But the trick is how to steer it, how to operate it, and how to build it, obviously. So still, what is quantum speedup? you have the input and the output. In a classical world, you would need to go through the arc, or go along the arc. In a quantum world, you can go into the sphere, but if the path is longer, you don't have speed up. But you can take a shortcut through the sphere in the shortest way, and that's quantum speed up in the very simplest case. So that is, we use these excess dimensions to gain speed up, to have less operations, to go from the problem to the solution. Okay. So some of you might have heard about the D-Wave quantum computer or quantum annealer. It cost about 10 million. I think nowadays a little bit more than 10 million. It has about 2,000 qubits, and it's huge. It's like 10 square meters in area, and it's 3 meters tall. And yet, it hasn't been proven that there's quantum speed up. So you might say, okay, why to spend 10 million on this machine, and it's not even guaranteed that we get speed up? Well, the answer is that it's not what the tech can do now only, but it's what it can do in 5 to 10 years from now. So I also already explained it can be an important factor in the cybersecurity. There are also ideas how to use it in some other computational problems like linear algebra. And it can, if we can do simulations of molecules with it, we could find ways to synthesize in a more efficient way chemical compounds such as fertilizers, and think about new materials. Could we actually start to simulate the properties of materials in a different way? Could we help our artificial intelligence? These are all questions that people are now searching for answers, and there are already partial answers, some hints that we can do this. One idea which has been sort of tested in a very small quantum processor in a lab is called this quantum cloud computing. So the idea here is that, typically when you have your classical computers in the cloud, if you ask them to solve some problem for you, you have to trust the provider of the service, so that the provider of the service doesn't leak your data out. If a bank wants to do some sort of analysis on their banking data, they probably wouldn't trust anybody to give all the account numbers and balances to some random company. However, in a quantum computer, because what I didn't tell you is that when you measure the qubit, it always latches into 1 or 0. So basically the superposition is destroyed. So basically what you can do is, you can send the provider of the service, you can send a state, and you don't tell what that state was. You just tell, okay, do this, computation on the state. And if the provider doesn't know what the state was, he doesn't really get information about your data. If he tries to measure it, he will change the data. And that's why you can they will do blind computing on the input, and they can't tweak the data or even get information out of it. So that's something that might help information security in the future. Well, something that is already there, I don't know how many of you knew about it, but for more than 10 years, there has been a commercially available quantum key distribution sort of system. There are many companies nowadays. ID Quantic from Switzerland was the first one to bring this into market. It's basically 2 of these kind of units. You put them into a 19-inch rack, and then you connect them with the optical fiber. And well, that's what you would do in a usual optical network as well. So it's not any different. What is different is that instead of very intense pulses of light, these boxes, they send single photons of light. arranged in a specific way. In a way that, if you capture the photon, you have to measure it, and that measurement disturbs the communication. So you always know if somebody's listening to you or not. And if somebody's listening, you cut the transmission. This line is compromised, we go to another line. So the principle of quantum key distribution, in principle, it cannot be eavesdropped. Not even if you had a quantum computer. This is one of the questions I typically get. What if you have a quantum? Can you eavesdrop quantum key? You can't. The principle is, proof of eavesdropping. Of course, the implementation can have faults. If you have, faulty components or somebody hacks into your box in a classical way, of course, then, you can eavesdrop it. But you can't listen. If you listen to the transmission in between and everything works fine, then you will always be noticed. So these kind of boxes, they already exist around the world, in Finland even. And some instances are very interested in this because now if the quantum computer would be built in the next 10 years or more, some data would be compromised. And, some people might have recorded data, and then they think when they have the quantum computer, they will decrypt it later. So this is why some instances already now say that, okay, we don't trust anymore the RSA, we don't trust some of the protocols, we rather use the quantum key distribution already now. Now I want to tell you a little bit more about the difference between the universal gate-based quantum computer and the D-Wave quantum annealer. So the quantum annealer I talked about little, it has like 2,000 qubits at the moment. However, these qubits have very short lifetime and you can only do very dedicated computing with them. The logical universal quantum computer that you can actually use to run the Shor's algorithm has much less qubits. Nowadays it's 20 that has been published. 20 that work well. And you can do any logical operations. It's basically like in a normal computer. You have logical operations and then you apply them and then in the end you get the result. And they have long qubit lifetime because the qubits have to live long for them to keep the quantum information undestroyed until the end of the computation. So what has really, why is it now so big a hype, that quantum computers are, coming? It's exactly, one of the reasons is the qubit lifetime. That has been increasing exponentially along the years. So here you can see the first qubit lifetime before 2000, it was just a nanosecond. And now it's been going up and up. And now we are in the position where the lifetime is not anymore necessarily the bottleneck. So it's not necessarily making you anymore so much errors that you couldn't do the computation or more errors than you would get from other sources. So that's the really great development here that has employed the big sort of fuss that now we can start to build large-scale quantum computers rather than just single qubits or 2 qubits. So what you need in the end is called quantum error correction. Because the qubits will anyways have some error. It might be 1 error in 1,000, 1 in 10,000, 1 in million, but they will have some error, which is non-negligible. If you want to break the RSA, you need so many gates. So it's going to take so many clock cycles that error will eat you up in the end. So in the end, you will need quantum error correction, which means that instead of doing the computation with single physical qubits, like each of these balls is a single physical qubit. That's the circuit in your computer, a single circuit. You group them into these groups, and you say, okay, this group of qubits, I will use them as a single logical qubit. And I will sniff the error. I will measure whether there is errors in there. I don't measure the state of the qubit, but I measure whether there was errors. And if I see errors, I can correct for them. And the larger groups you use, the higher fidelity logical qubits you will get with the same physical qubits. So that's the way to go to large scale. We compromise on the size of the memory, but we get higher fidelity. And some of the open problems I've also listed here. So we still need better ways to reset the qubits. You know, that's currently done at a little bit better than 99%, maybe 99.5, 99.6. But we want to get to 4 nines so that we don't need as many physical qubits in the logical qubit. We also want to study how can we get very extreme gate accuracy. So again, talk about 4 or 5 nines of gate accuracy. And how about the power consumption at the low temperatures? You know, these chips that I showed you, they work at 50 millikelvin or 10 millikelvin temperature, very close to the absolute zero. And the power you dump in there can start to be a problem when you have like million qubits, for example, or billion qubits. So at some point, this has to be taken care of. So in my research group at Aalto, we think about these problems, and we're trying to build a quantum processor and try to solve some of these problems. Of course, there's lots of engineering work that has to be done to get a working large-scale quantum computer. You know, this requires even more money. You know, it requires a lot of money to engineer everything. It's a huge effort. But as I said, now when these quantum computers starts to appear, the software becomes even more important. Like 15 years ago, I was thinking about this compiling these quantum algorithms, and I wrote a couple of scientific articles about it, and I thought it's kind of very far in the future. But now the software, there starts to be companies doing software, so now the software really starts to be also more important, and you might be more interested in the software than hardware, because the hardware has all sorts of quantum physics things in there which are pretty hard to get on hold to, but the software is much easier. You know, of course there's also a quantum thing there, but it's much easier to learn that. Okay, now I think I have 2.5 minutes for questions. So I'm sure here is a question. Could I have a mic here?
With all those challenges taken into account, if like, in rough estimation, how soon do you think we will all switch to the quantum computers?
Well, that's always the question you get, and I wouldn't say that we would switch to quantum computers soon. The quantum computers, as I explained, we know how to solve some problems efficiently with a well-working quantum computer, but we don't know, whether it will be better than the classical computer in everything. And most likely, it will not be, at least in our lifetime. But certainly, maybe the proper question is that when do we get quantum advantage in computing? When is the quantum computer so large in memory and so high fidelity that it can solve some practical questions that are of interest? That is a difficult question. I always say that it takes more than 10 years. It's like fusion is always coming in 10 years from now. But it certainly, there has been tremendous progress, and that's a difficult question. But there are many technical challenges that still need to be solved, and unfortunately, I can't see in the future. But certainly, it is in a point that it looks like that it will be there. We don't see any major hurdles. We don't see any fundamental problems. It's just a lot of work, and it depends on the amount of course, also about the amount of money it's invested in it. Okay, still one question.
Yeah, going back to the metaphor you proposed with the quantum sphere, it seems that to go from point A in the classical realm to point B in the classical realm through quantum computing, the chances of actually getting quantum speed up is close to 1 to infinity. So how much does it give you a headache?
Well,
Think about
okay. Well, that's a nice sort of okay. In that example, it was not actually 1 to infinity, but maybe 1 to 100 or something. Because if you take the area. But anyways, but that's a very good question. The quantum world is so high dimensional. It's in reality it's so high dimensional that little changes of these angles can take you completely out. And that's exactly where you need the quantum error correction. You don't want the errors to accumulate. You want to kill them. And fortunately, there is the quantum error correction invented. And it's exciting to see how soon that will be implemented efficiently. But there are good groups in the world working on that. Okay, thank you. Now my time is up.